Good afternoon, everyone. No? Last meeting, I've shown you the assignment. I've discussed the assignment with you, and I've shown you a program that is used. No, I've shown you a program that is used to compute the grade, to convert the grade into a score. Okay, and then determine whether the score, the computed, rather compute the grade from a score and determine whether the computed grade is passing or failing. I've already uploaded them, no, to our Dagger site. You can check them out. Okay, it's here, the grade computation. Uh, yes, and I only missed the last meeting, no, for the recording, but I have recorded them. So anyway, I'll upload them later this week. So there's grade computation, no, and then answers. Did I upload the answers to the exercises? Let me show you that already, no. Programming exercises. Uh, I haven't shown you the. I haven't been showing you the. No, I'm going to grade. I'm going to check your assignments, no, and those. Anyway, if you're late, you can still pass by email, but next time around, we'll not allow no passing by email because it's very hard to grade, no, when to pass as when assignments are passed by. Any questions?
Sir,
Questions?
sir, yung assignment ko, sir, kaya hindi ko pa na-update, sir.
I-email mo na
Ay,
lang. Okay, close na. The assignment is already closed.
I
And I,
mean, i-update pa ba yun, sir? Kasi 'di ba last time kasi mali yung loop, sir.
only the I will update. Yes, I will update the ano. I will update the example. Okay?
I mean, i-change pa namin yung answers namin doon.
Don't need. I'll adjust myself. Okay? I know I was wrong there. Okay?
Okay, thank you, sir.
No need to adjust for my mistake. No. So I have there the grade and then the answers na I'm going to upload na lang together uh, with the recording no of our last meeting. Okay? Do you follow? So andito na. Okay. Most probably we'll have our first formative test by the second week of August. Okay, be prepared for this. Second week of August. This week is our last week. Okay, I'll give you. Okay, any questions now? The coverage will be the whole set of topics of history of computing. Do you follow? Okay, I'm going to give you a practice test over the weekend so that you can practice before the test. Okay, any questions? Prepare for the second week of August, no, for our first formative test. And then I've shown you the the descendants of Charles Babbage, of Charles Babbage, no? The engines, no. So ito yung mga these are also the pre-electronic. Most of them are the pre-electronic engines, no, like the bomb, which was used to decipher, no, in cryptology, because the bomb was developed during the Second World War. No, it's uh, it's not programmable. No, it's only used to decrypt no, encoded messages. Z2 was the binary floating point. This is very important because this is a computer. We do not have, unfortunately, there's very little document about the Z2. No? But it's very similar to the analytical engine, except that this is binary, and the recording is by tape, no, by tape, and it was not put to use because it's not Turing complete. The ABC computer, invented in the U.S. in Iowa State University, John Van Vincent Atanasoff and Clifford Berry. I don't have to open the source, no, but there's so many sources, no. This is a binary computer, no. This is important because this is the first binary machine. It's not considered a computer, but a binary electronic binary machine. No? this is significant because this is one of the first machines. No? Paano ba natin ito ano? This is one of the first machines that were invented using regenerative capacitor memory. So during that time, there was a simple device, no, that resembles our modern computer memory, capacitor type, no. It was first invented in 1942. So which computer has the first capacitor type or regenerative capacitor type memory? It's the ABC computer from Iowa State, no, 1942. Colossus Mark I in the UK. There were two Mark I's, no? One in the UK and another one in the US. Harvard University, developed by IBM, by Howard Aiken, no? In 1944, during the towards the end of the war, no? They invented an electromechanical machine which resembles Charles Babbage analytical engine. Okay, purely mechanical. And there's a jargon that was coined here. It's called the bug. Okay, Z4, the first commercially produced, no, computer. It's in 1948, and in 1948, there's already there's the dawn of the stored program concept. Okay, this is I don't there's no documentation. I think this is stored program concept. Let's find out. Floating point na ito, no? 22-bit floating point, not 32. So that's a little weird. So there's no specification which tells that uh, this is a stored program computer. No? So there's no such sets. Okay, okay. So Harvard Mark I, ito yon, no? By Howard Aiken. Okay, and then the next significant is after the war. This was Eniac, developed in the US. No? It is a decimal computer. This is significant because this is the first electronic implementation of the computer by Charles Babbage. No? So it uses vacuum tube, electronic na, vacuum tube flip-flops. Okay, we will discuss flip-flops, no, later in the course. No? And then by 1948, at the end of the war, no, there was Manchester Baby. Okay, from the UK. It's a binary computer, not no more decimal. It's an electronic binary computer. It's a Turing complete. No, like these are the Turing. From then on, computers are Turing complete. No? And uses cathode ray tubes. And Manchester Baby is the first computer with an electronic keyboard, with a keyboard. Okay, first computer with a keyboard. Okay, so ito yon, no? The pre-electronic, it's the same, no? Most of the pre-electronic period are computers that which descend from Charles Babbage, no? Bakit ayaw mag-open? Okay, we have a problem with Ziegler, but more or less they're the same, no? The descendants and the pre-electronic period, okay? Ziegler is slowing down. So anyway, no? Now, so many things happened during the war, especially during 1950s. Let's introduce another important figure in computer science. Is by the name of Alan Turing. No? Alan Turing is the father of theoretical computer science because he invented theoretical computer machines. No, so in fact he contended with John von Neumann. No, John von Neumann was also about during that time. No, that he invented everything. No, according to Alan Turing, he invented everything, even John von Neumann's machine, but he only developed theoretical models. No, he's a very smart mathematician. No, he was the first to rediscover, one of the first, no, to rediscover the analytical engine, because from 1877, or rather 71, when Charles Babbage died, nothing developed after, no, the analytical engine. No research developed. However, it was rediscovered by Alan Turing in his book, no, the rediscovery of uh, during the 1950s, exact 1950, the year 1950, in his book Computing Machinery and Intelligence, no? So the father of artificial intelligence and modern computer, rather theoretical computer science, Alan Turing, no? In his book in 1950, the book was entitled, no, Computing Machinery and Intelligence, Mind 59. I don't, maybe this is for pages 433 to pages 60. I don't have an actual copy of the book, no, that invented the Turing test for the imitation game. Now, it was then that Alan Turing completed the Turing test, the criteria for Turing test, to find out whether a machine is finite or not. So ito yung kanyang comment. The idea of the digital computer is an old one, by Charles Babbage, a location professor of mathematics at Cambridge. No? Planned such a machine called the analytical engine, but was never completed. Although Babbage had all the essential ideas, no? He had all the essential ideas for a computer. His machine was not at that time very attractive, such a very attractive prospect. So nobody developed interest, except of course Ada Lovelace, no? Okay, that's, so actually, according to Alan Turing, it was already a complete computer by itself, but nobody paid attention to it, so that's why it died a natural death, no? The speed at which would have been available would be definitely faster, no? According to him, if it was developed, no, the speed of which that the would have been, the speed of computation would have been definitely faster than a human computer, than a person doing computations, something like 100 times faster than the Manchester machine, the Manchester baby, itself one of the slower of the modern machines. The storage was to be purely mechanical, using wheels and cards, no? Because that was the invention of Charles Babbage. So this was during the 1950, no? When Alan Turing rediscovered the work of Charles Babbage. So imagine the gap from 1870 to 1950. How many years? About 80 years, no? 79 years. Okay, 79 years of nothing, no? So who is Alan Turing? Alan Turing is the father of the uh, modern computer science, no? Theoretical computing. Theoretical computing because he invented machines using models, mathematical models, no? Graphs, using mathematical graphs, no? And then he also invented his own machines, no? But not physical machines, no? So his primary work was on crypto analysis, because he was hired by the UK government to break Enigma codes, no? So ito. Alan Turing was considered to be one of the smartest mathematicians of all time. Okay, there are many references that tell you that, no? One of the smartest mathematicians, no? He is the father of artificial intelligence, father of computer science, no? Father of computing, no? Okay. Unfortunately, like Ada Lovelace, he passed away at an early age, no? 1952 when he started. Okay. He died on 1954, 4 years after he rediscovered the engine. But fortunately, he left a lot of legacy in computing, no? And now, for the computer science students, you will have one semester of automata theory. You will study all the machines invented by Alan Turing. Okay? Any questions so far? So Alan Turing, no, the father of no, the mathematician who invented artificial intelligence and modern computer science, no? Theoretical computer science, theoretical computing. He also rediscovered the work of Charles Babbage. Okay, you follow? Okay, Alan Turing. So any questions so far? Any questions? So what were the improve improvements during the pre-electronic period? In 1884, remember, no, when the US was after the U.S. Civil War, no, they started doing census. The American inventor Herman Hollerith, no, invented a punch card tabulating machine, okay, and established a company for counting, no, who produces machines for counting. In 1904, the vacuum tube diode was invented. So after the invention of the vacuum tube, many other devices were invented, like the radio, the TV, telegraph, no, and so on and so forth. In 1911, no, Herman Hollerith in the US founded the Computing Tabulating Recording Company, which was renamed IBM in 1924. The company with we are going to study one of the computers, IBM 701. Okay, he is one of the important figures in data processing, Herman Hollerith. In 1912, no, the first electronic powered mechanical analog computer, the Argo clock. No, it's a mechanical analog computer, no, in 1912, no, from Great Britain. Now, in 1931, there was the invention of the general purpose, no, differential analyzer, 1928, and prime and later on, no, in 1942, no, ito yung ABC computer to 1937, followed by the Mark I, and then later Conrad Zuse, no. And in 1945, the next significant invention was introduced. John Mockley and J. Presper Eckert, Penn State University. They built the Eniac. Actually, they built it during 1943 pa, but it was introduced in 1945. It's called Eniac, Electronic Numerical Integrator and Computer. It was a decimal-based computer with close resemblance to Babbage analytical engine. Okay, let's look at the what's unique about Eniac. Let's look at this. Let's close the unnecessary things. Now I think there's a video about the Eniac documentary. The Eniac was developed during the war. Now, by the way, before we proceed, I have come across a very important page in history. Okay, what happened in history years ago, July 25 and 26, okay. There was this, okay. IBM was granted the first patent, in 1911, okay, because it was introduced in 1912, 1800 siya na established. In vitro. There was in vitro during 1978. Now, in 1981, Vimeo was like Atari. It's a gaming computer. Software engineer was born, the inventor of Vimeo. Now, Apple released Mac OS X 2012. Okay. Apple released July 25, 2012. Amazon Fire Phone was released. Have you seen this? The Amazon Fire Phone. Now, China ended its gaming console ban after 15 years. It started creating games, console games like the PSP, is a console game. Fortnite. Do you know how to play Fortnite? It was released in 2017, Fortnite. And then we don't know this. 1983, today, Famicom home computer and video game was released in Nintendo Japan. Nintendo, was developed in 1983. 1995, July 26, Amazon was opened. Mozilla was formed, no, after Netscape, the browser. Mozilla was founded 2003. Twitter in 2006, no, July 26. Android 2011, no, 2015. Impact Team, what did it do? In 2020, no, Twitter was hacked. Okay. 130 accounts. There was no was hacked. July 26, no, last year. We didn't know that. Okay. The Eniac computer, is it already there? I'm sorry, no. Yan. Okay. So it was the first electronic computer, no? It was the first electronic computer used for general purposes, invented by John Presper Eckert and John Presper Eckert and John Mockley. J. Presper Eckert, no? John Presper Eckert at Penn State University, no? And it was intended for the use of the army. Constructed, that's right, 1943, and was introduced in 1946. No? This was the Eniac, no? It's the picture of the Eniac. No? How many transistors it used? Vacuum tube transistors, no? Do you follow? No? So let's have a comparison. So you can watch this, no? It's a video on the Eniac documentary, no? Do you follow? You watch this video yourself, no? Okay. We don't have time for this, but this is very useful.
Like digital computer
No.
ever made.
You watch this, everyone, no?
This originally silent film has been carefully edited
Okay.
to read.
We will include items there to our exam. Okay. It's a very it's an enjoyable video, no? It's very old but very historical, no? Ano, okay. So let's look at the design of the Eniac, like we did, no? What's the difference between the Eniac and the ganito, no? Ito. So 1943, no, introduced in 1946, completed in 1945. Okay, the input was possible from an IBM card reader, and IBM punch card was used for output. So let's look for an IBM card reader. So you know the history of card readers now. They come from Jacquard's loom. Okay, it's like this, no? This is a card reader. You place a deck of cards. Punch card part used in the IBM 701, no? One of the first, no? It looks like this, you know. You will have a deck of cards. You place it somewhere. It resembles. It's like the modern version of the Jacquard's loom, no? Where the punch cards are processed individually. Here's an example of a virtual card. Of a card, no? Ito, no? This is a card, no? This is an 80-column card, which can store 80 digits, no? 80 digits. You see, for each record, one row is one record. Do you follow? Okay. So the input is taken from a card reader and the output is on a card punch. So it's really like an electronic version of the Jacquard's loom. Do you follow? No? Because there's already electronic technology during that time, because there were already vacuum tubes. Remember 1911, there are already vacuum tube diodes. So there was already a punch card reader from IBM and a punch card writer also from IBM. While Eniac had no system to store memory in its inception, there's no memory during the first version. No, these punch cards could be used as external memory. However, in 1953, a 100-word magnetic core memory, magnetic core, no, it's an ion type, no, depending whether the magnet is charged or not, no. is magnetized or not, it can store by values, decimal values. In 1953, a 100 word magnetic, 100 word, which means that 100 numbers. They follow very, very small memory, 100 number word magnetic core memory built by Burroughs was added to Eniac in 1953 because originally there were no memory devices. Eniac used 10 position ring counters to store digits. So 10 position, it means that it can have 10 digits, 10 position ring counters. What do you mean by this? No, there are 10 counters. I'm sorry, there are 10 counters. No? It had 10-digit accumulators used for tens complement representation and could perform 5,000 simple addition or subtractions between any of them, and a source. So it can do 5,000. It doesn't say how long it will take, but it can take 5,000 simple addition and subtraction. It had 20 accumulators. What do we mean by the accumulator? This is the first device invented in Eniac, the accumulator. Okay. The accumulator, let's look at the analytical engine. In the analytical engine, the processing unit had 3 registers, 2 ingress and 1 egress. By ingress, we mean input. So input is stored in the ingress registers, and output is in the egress. Now, the Eniac inventors didn't like this because this is inefficient. Why don't we use a register both for input and output? Do you follow? Do you follow? So they coined it accumulator. When we say 20 accumulators, it had 20 registers that each can be used for both ingress and egress. Do you follow? Do you follow? Okay? So 20 accumulators. It's like 20 ingress and egress at the same time. Okay? I think we can have wala na tayo nitong programming, no? We don't have the instruction set. Okay, sorry, no? Sorry, no? Yeah. So, I'm sorry, na-distort yung aking wire. We don't have the instruction set of Eniac. So, we will not have programming for Eniac. So, programming in the Eniac was done manually by setting switches and connecting wires on a plug board. The program is written on a paper. Okay? It does not have a programming manual, but it was Turing complete. Okay? So, it's like the electronic version of Charles Babbage's analytical engine. Only more powerful because it has 20 accumulators. It also, like the analytical engine, it uses fixed point decimal. Okay? The program is stored sequentially on punch cards. In the Eniac, programming is done by setting switches, although input is taken from a punch card. The programmers are all women. The programmers of Eniac are all women. Okay? 5 of them. Programmers. Let's look. They wrote, what program did they write? We don't know. Okay. But Eniac was developed for the US military. Okay, so most probably military applications. Okay. Okay, so these are why all women? Because this was done during the Second World War. Most men are out in the front line. So, okay, they follow. Ito sila, mga women. This is the Eniac itself. What's the application? It was developed by Prosper Eckert and John Mockley for the US ballistics. Maybe they are going to use this for firing missiles. Missiles. They follow? Okay. We will not program the Eniac. Okay. Anyway, this is the important part. We know the evolution of the Eniac, which the hardware, by the way, the hardware of the analytical engine was never implemented. Eniac is composed of 18,000 vacuum tubes, 1,500 relays. A relay is like a transistor, 10,000 capacitors and 70,000 resistors. It occupied 1,800 square feet. 1,800 square feet. About an office, The inventors, no? Charles W. Babbage, France. No, this is not France. This is I'm sorry, this is UK, no? I'll edit this. This is UK. While Eniac was invented in a university, no? Iowa State University. Iowa ba? Yes. Because Penn State, no. Let me check, no? Sorry, no? Sorry. This the this is what I don't like about the new Daygler, no? It doesn't bring you to where you left off. You have to search again. If it does, it takes a long time. Mina na siya. Penn State. I'm sorry, it's not Iowa State. Saan yung what was discovered in Iowa? It was the ABC computer. Okay? The ABC computer. And in IBM, or rather in Harvard, it was the Mark I. Okay? Penn State University. That's where it was invented. The ABC computer was in Iowa State University. Okay. John Clifford Berry and ABC Berry and Atanasoff. John Van Vincent Atanasoff and Clifford Berry. That's ABC. Excuse me, will you excuse me a while? I'll just have to check. Okay, I'm sorry. No, let's proceed. So it brings us to a new topic, no? A very important topic, which is the stored program concept. Okay, who knows about the stored program concept? Can you tell me what it is? Okay, ito. The stored program concept. Who's the inventor? The physical inventor is John von Neumann, but the model was also invented by Alan Turing. Okay? But the physical design, officially, no? John von Neumann. Okay, 1945. That's also about the time of Alan Turing. Alan Turing was doing cryptology, and the Turing machines were invented during 1950s, no? Okay, during the 1950s, one of which was the rediscovery of the analytical engine. Can you see the, no? And anyway, you can open this, okay, in your PC. Where's Van Neumann? Also is associated with the design of the Eniac. Do you follow? In Penn State University. He's a consultant to the design of the Eniac. When Van Neumann looked at the Eniac and also the analytical engine, he noticed a very significant, flaw in the design. No, it was basically the storage of the program, because remember, Eniac and the analytical engine originally had no memory, so the programs are running on the punch cards. Do you follow? No, if you write a program, you will put them on the punch card, no, and then the punch cards will be read one by one and will be processed individually as the program is executed. That's the same thing in the analytical engine, right? The cards are running on the Jacquard's loom and they are processed individually. Uh, Von Neumann didn't like the idea that the program will be running on the punch card or on the input device. Okay, ito yung this is what Von Neumann didn't like in in the in the analytical engine and the Eniac, because programs are running on the punch card, which he didn't like. No, so the IAS machine was a binary computer. It was a design created by Von Neumann in 1945, and which was supposed to be a binary computer. It was designed to be a binary computer with 40-bit words, which means that for the ENIAC it's 20-bit, 20 decimal digits. This time this is in binary. So 40-bit words using 2-bit instructions in each word. It's strange, no? The memory was 1 kiloword. Okay, 1 kiloword because it's 5.1 kilobytes because 1 byte is 8, right? And if these are 40, about 40 bits will store divided by 8 will store you 5, right? So 5 times in terms of a byte. No? Negative numbers are represented in 2's complement format. We will study the 2's complement format later, when we study binary numbers. So this is very strange. Why? Because this is 40-bit words. Unlike it has 20-bit decimal or 20 digits 20 digit numbers. The ENIAC has 40-bit words with 20-bit instructions, so which means it's strange, no? Because the word and the bits are different. Okay? You follow? So here's a comparison between the analytical engine and the stored program concept. In terms of the number system, 40 decimal digits yung analytical engine by Charles Babbage. Now, it has 40 decimal digits and it uses fixed point decimal. Okay? And the IAS uses floating point binary with 40 bits. Okay? 40 bits. Incidentally, the same. 40 bits. I don't know if it was intended to be the same, but this time it uses 40 bits. Okay? Do you follow? Do you follow? No?
Yes, sir.
Okay. So, then the processing unit. The processing unit for the analytical engine is this. It has 2 input registers and 1 output register. Now, the IAS computer has divided the mill into an arithmetic logic unit, which means the arithmetic is done by 1 unit, and the branching or control, you have CF and CB, right, in the analytical engine. We also have control unit, in the IAS, but it's split into a different unit. We'll look at that later when we study binary design or digital logic. Now, this time it uses one multipurpose accumulator register patterned from the Eniac. Do you follow? It has one accumulator register which is both used to do input and output. Okay? And it uses a multiplier quotient register, which means that during multiplication, the first multiplicand is in the accumulator, thus the multiplier is in the MQ register. During a division, the MQ register stores the divisor. During subtraction, the MQ register stores the subtrahend. Diba? Subtrahend ba yung negative? The negative part is stored in the MQ register. Do you follow? I hope you follow, because we will make programs for this computer. Okay? It has general purpose registers, which means it can be used for load and store at the same time. Okay? It can be used for load and store at the same time. It has a memory address register. What is a memory address register? It points like in the analytical engine. When we say analytical engine, when we say L001, what do we mean by that? 001 is the address. Okay, so the IAS computer uses a register to store the address before loading and storing. Do you follow? Do you follow, everyone?
Yes, po, sir.
And then there's a memory data register. What's a data register? During a store, when you say S001, 1, the value 1, which is data, is stored first in the data register before it is transferred to memory. Do you follow? No, so meron siyang, there are new registers introduced, which means that you do not access the memory right away, but you have to store them into temporary registers. Unlike in the analytical engine where you load and store directly to memory using the mill. In this case, no, the control unit or the CPU does not access memory right away. It has to load them in a data register and an address register. It has an instruction buffer register. What do we mean by instruction register? During a card, no, when you say times, divide, no, the instruction, mul, jump, also is stored in a different register. Unlike in the analytical engine where there's only one source for both input and data. Okay? It has a program counter which points to the next instruction. So this introduces us to a new concept. Why are there temporary registers? Because programs are not executed directly from the input device. Do you follow? They are stored in the memory first. That's called the stored program concept. So input and output from in the IAS engine is in the Jacquard loom. In the IAS, no, program or data is read into memory from the input device, which means you do not execute it directly from the input device. Do you follow? Can we, see, program or data is read into memory from the input device or secondary storage under the control of the CPU. Output devices are used to output the information to form a computer. Do you follow? So, ganun ang concept niya. Programs and data are read into memory. How are programs executed? In the IAS, programs are loaded sequentially via the Jacquard's loom to the mill. Do you follow? And data are stored separately in the store or variable. No? Now, a different concept was introduced by John von Neumann. Here's the concept. First, programs are loaded by batch from storage to memory, which means you do not execute them right away. That's the same case today. It applies until today. When you run Windows, Windows isn't run from the hard disk directly. What you do is, it's loaded first into memory before it's executed. When you run a word processor, the word processor doesn't run from your hard disk. It's loaded into your memory and it's executed in memory one by one. That's called the stored program concept. No? Instructions and data are both stored in memory at the same time. That's the main concept of the stored program. Okay? Instructions are data are both stored in memory. Unlike in the design of the analytical engine, the instructions are in the Jacquard loom. They're in the cards. Even in the early computers, no? Even in the early computers like the Zeus, no? The programs are running on the card reader. Okay? For von Neumann, no, that's wrong. According to von Neumann. Let's not run them separately. Let's store them, both instruction and data, in memory first. That's called stored program. Any questions? This is very important, no? You should be able to distinguish the stored program concept. Instructions are fed sequentially from memory to CPU during program and execution. Now there goes another jargon, fetch and execute. Okay? What do you mean by fetch and execute? It's a cycle that is used to process a program in memory. Okay? So, mali na naman dito, no? The program was the inventor was Charles Babbage in UK, and IAS was invented in 1951 by John von Neumann, no? Princeton University. Okay? They follow in the US. Because after the war, all the developments came from the US. Okay? Any questions so far? Because we will introduce the IAS instruction set. Okay? Let's edit this first. Okay. UK. Okay. Any questions so far? So now we will study a new computer. Okay. It's not very new because it was invented in 1951. Okay. All this is very important because all computers were patterned after that. No, it's called the stored program. Even computers nowadays are all stored program computers. No, you may ask, will this become obsolete? Yes, maybe no. Because the main contention of Van Neumann is we cannot run the program in in the input device. Why? Because the input device is very slow. Do you follow? Do you get my point? No? If you run the program from the input device, it's very slow. Whereas if you load it into the memory first, the memory is much faster than the device. So it will run much faster. The fetch and execute from memory is much faster than the fetch and execute from the deck of cards. Do you get my point? Diba? Nowadays, it still applies because if you run a program from the disk is much lower than the main memory, right? That's why you have to load your program from your hard disk to your memory before executing. The OS does that for us now. However, when time comes when hard disks are as fast as memory, maybe the stored program concept will not be needed anymore because Intel has introduced a new hard disk lately, no? Which runs very fast, which could be introduced in the next two decades, no? New Intel SSD. Can we Google that? Sideline lang muna tayo, no? Sides. The new invention, if you have read that, no? Intel will introduce a new SSD. No? Okay. Okay. Ito. This is a very fast SSD. You know what an SSD is, no? SSD disk. No? It's supposed to have been introduced already, no? But this is still very expensive. This is a new disk which runs very as much almost as fast as memory. Okay, it's only 4 times slower, no, one fourth 25% of the speed of memory. So if it runs 25%, it's short 75%. Maybe in a few years it will be 50%. In a decade it will be 100%, which means that in the end, no, the future will come when hard disks will be as fast as memory, as RAM, and the store program concept will not be needed. Okay, that's only a speculation, no? Because that's the main reason why John von Neumann in 1951 contended that programs should run in memory, okay, not on the secondary storage device. Do you get my point, everyone? No? Okay. Programs should run in memory. Yun ang sabi ni ano. Ito. Now, this is the ano. Can you read this? You can download this if you like. Everyone? Any questions? Now we're coming closer to a new computer. This is because this is a real computer now. These were invented into real machines, no? These were invented into real machines. Okay. Can you see that? This is the instruction set. Now, before we only have N, L, S, what do you have? CF, CV, CB. We have times, divide, minus, no? Okay, do you follow? Now, here's the no. Now, since it's binary, the programs will come into versions, no? The binary version, which is the opcode, and the symbolic representation, which means that The symbolic representation is the program shown in written paper. You follow? So that, but before they're transferred to the computer, it's transferred into its original operation code, which is this designated operation code. No? So for example, load MQ. In the analytical engine, we have load. In the IAS, we have load MQ. This means that we transfer the register MQ to AC. Remember, we have the accumulator register. The accumulator register is the register borrowed from the Eniac. Okay? Do you follow? Load MQ, which means we transfer data. We don't say load AC MQ because by default, it will go to AC. Any questions so far? Okay. Load MQ, MX. Okay. Transfer contents of memory from location X to MQ. It's like load 001. Diba? It transfers the register 001 to the ingress axis or 1 or 2. Do you follow? Do you follow? Dito, when you say load MQ, the variable in M of X, X is the address, will be transferred to the register MQ. Okay? Do you follow? You can think of MQ as the ingress axis. Any questions so far? I hope you're listening now. We'll end at 3 o'clock. Anyway, we'll just finish the instruction set. Whether we reach 3 o'clock or not, we'll terminate. Okay? We're having too much. Okay. Take note that this is the same load of the analytical engine. Okay? Iba lang yung terminology. Okay? We say store MX. Okay? This time we are going to transfer. This is not from the MQ but the accumulator. Do you follow? So in the analytical engine, when you say S001, we store the egress to memory. Right? In the IAS engine, when we say store MX or store M001, we transfer the accumulator because it's both ingress and egress to memory location X. Do you follow? So tingnan, do you see it resembles the analytical engine? Right? Because it came from the analytical engine anyway. No? Halos pareho. There are similarities. Okay? Any questions so far?
None po, sir.
Now, we have load MX. This is almost the identical load of the analytical engine. When we say load MX, we will transfer MX to the accumulator. Now, in the analytical engine, we say transfer to ingress axis 1 or transfer to ingress axis 2, depending on the location. But this time, you can think of MQ as the ingress axis 2, AC as the ingress axis 1. Halos pareho lang. Kaya lang, when you say load to ingress axis 2, you say load MQ. When you say load MX, we transfer to the accumulator. Do you follow? You have two registers, accumulator and MQ. In the IAS, we have ingress axis 1 and ingress axis 2. Okay? Now, we have load minus MX. We load the negative to the accumulator. It's just like load, but it converts to negative first by 2's complement representation. On the other hand, we say load absolute, which has a different opcode. Okay? Load absolute, we remove the sign and before transferring to the accumulator. Okay? And then we say negative absolute, we mean we get the absolute and we convert it to negative. Okay? So the negative is still negative, the positive becomes negative. Okay? Do you follow? There are many applications for that, no? In the IAS, rather in the analytical engine, we don't have a jump, but we have a CF and a CB. In here, we have a jump, no? We have jump to X, no? X is the address. Do you follow? Jump 2000, or rather, shall say 500, which means we jump to address 500. However, there's a strange thing about the design, which is now absolute, no? When you say jump to X, there are two places in X to jump. Do you follow? There's a left X and a right X. Left side X and right side X. Why is that? Because the words are 40 bits, but okay, the instructions are 20 bits. Only half the size, which means in one memory word, 2 instructions can fit. Do you follow? Do you follow? Which makes for a very complicated jump, which means when you jump, you don't just say jump to that address. You jump to the left of that address or you jump to the right of that address. This is the flow of the design. No design is perfect, no? But it's understandable. Why did he invent it like this? Because memory during those days was very expensive, no? If you are going to fit only one instruction in a 40-bit word, the other half is wasted. Do you follow? I hope you follow, no? You have a 40-bit word. If you are just going to fit one instruction there, only half of it is used. The other one is left wasted. It's never used. So, according to Van Neumann, let's fit 2 instructions in one word. Memory is very expensive. Well, cost leads to complication, right? Right? Because when you jump to the left and you jump to the right, you make a very complicated jump. Okay? Unlike in the analytical engine, you just say jump to this address, jump to 2000, jump to 1000, it's okay. But in the IAS, you say jump to 1000. Which part of 1000? To the left part. Okay? It's like go to place X, go to the left or go to the right. Okay? Do you follow? Now, there's a jump plus. The jump plus is like the opposite of the CF. Kasi jump minus yung CF eh. Jump minus yung CF. You can think of jump of CF, no? CF and CB in the IAS as jump minus in IAS. Binaligtad niya. Okay? Jump plus. Jump if the accumulator is positive, no? Doon sa ating sa CF, di ba? Pag mag-negative yung yung egress, positive yung then that's the jump. Do you follow? In the IAS, when we say jump plus, we only jump if the accumulator is positive. We do not jump if the accumulator is positive. Now, this is used for looping and branching. Kaya lang, our thinking this time will be opposite the analytical engine, because in the analytical engine, we are used to jump minus. Okay? Bakit niya binaligtad? I don't know. Bakit hindi na lang? Why not just jump minus para it's the same as the analytical engine? That's another question we can never know. The inventors have their own mind. No, they never follow. They invent their own. Okay. Any questions? We'll finish this, no, and then I'll introduce you to the programs. Next meeting na lang. Tapusin natin muna ito. Add MX. Add memory X to the accumulator. Do you follow? Whatever the value of the accumulator is, add it with the value from MX. When you say add the absolute value of MX. Sub MX is like add MX. Sub absolute is like add absolute, but it only does a sub. This time we have a mole. Okay? Ang maganda, meron tayong mole. In the analytical engine, we don't have a mole. A mole will multiply. Okay? And then a div will divide. But we have a divide, no? But according to there's a divide in the analytical engine. There's also a mole. Anyway, we did not study them. Left shift. We left shift the accumulator. LSAH. RSH, we right shift. What happens when we left shift? We multiply by 2. When we right shift, we divide by 2. Do you follow? Store MX. What's the difference between this store and that store? Sometimes you will have to store a number, and sometimes you will have to store a smaller number. So there's a store left and there's a store right. Do you follow? Because one word can have two instructions, no? Do you follow? So 12 bits lang, kasi meron pa tayong opcode. If you have 20 bits yung instruction, di ba? And the opcode is how many are this? Can we count this? 1, 2, 3, 4, 5, 6, 7, 8. So the opcode is 8. You have 20 bits. Only 12 bits is used for the value. Do you follow? Because the 8 bits are used for the instruction. Okay. So now we have coined another jargon. Okay. The first bits are called the opcode. The other bits are called the operand. No. The 8 bits here are called the opcode. The 12 bits are called the operand or the parameter. Do you follow? No? Address modify ito, no? Questions? You know what's an opcode? It's actually the binary code of an instruction. What's the operand? It's the parameter to the opcode, no? Which comes to the operation after the opcode. Do you follow? Opcode and operand, okay? Remember that, no? Remember that? Opcode and operand. Okay, any questions so far? I hope you distinguish, no? Okay. Nasaan na tayo? Okay. The IAS computer. We'll start programming, no? We'll discuss programming with the IAS engine next meeting. Okay? The IAS programs. No, we will discuss these programs. And like the analytical engine, you will have a programming assignment, okay, to write. And then we will program the IBM 701. Okay. I hope we can write programs for the PDP1, because the PDP1 is very close to the no. Here's a sample program, no? The IBM on the fourth factorial, okay? We have fourth factorial on the IAS. Okay? We will study this next meeting. So we'll study it like we did in the analytical engine. Do you follow? Any questions so far? So we will have a looping also sometime. Okay? Any questions? Everyone? Any
None
questions?
for me, sir.
Okay, so we will discuss the programming of the IBM, or rather the IAS computer next meeting, no? Wala na tayong time ngayon. It doesn't have we don't have time. We'll better start fresh next meeting. Okay. So if you have no questions, I will dismiss the class. Okay. Thank you everyone for coming.
Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you, sir.
See you next meeting.
Thank you, sir.
Bye, sir. Thank you.
Bye.
Thank you, sir.